Welcome to Special Right Triangles and the Unit Circle. This is going to be super helpful in preparing us for calculus because trigonometry is a large part of calculus in a sense that, we have to understand the basics of trig in order to succeed in calc. So whatever you do remember or don't remember from the unit circle, I will go over in a condensed way. So I'm not going to go into every single tiny proof or explanation of everything. If you do have questions on why something is the way it is, feel free to ask and I'll be glad to let you know, or maybe make another video, or you can look it up if you're interested. But I want to make this a quick video just reviewing the basics of trig. So you learned about special right triangles in geometry, probably a little bit more trig in either pre-calc or algebra 2. So let's take a look. What is the unit circle? The unit circle is a circle with a radius of 1 and a center at the origin. I have one right here. So here's our origin, and this circle has a radius of 1, therefore these 4 points are known to us, so we can mark them in. So those 4 points are known to us because we are going 1 unit out because the circle has a radius of 1. So these 4 points are pretty important. And the next thing that we know is we all can agree that a circle, if you go all the way around it, is a 360-degree angle. Basically, it makes an entire circle. So if we were to go halfway, that would be 180 degrees. Therefore, we can mark these 4 spots with degrees. So we start over here at 1, 0. This is like our beginning. And we'll call this 0 degrees. And then if we go all the way around, it's also 360 degrees. It's like running a race. If you've ever run like a 5K or something, a majority of them will start and end at the exact same spot. So even though it's at the same location, you're beginning, you run your race, and you end. So it's also 360 degrees. Okay, so halfway around would be 180 degrees. Half of that up top is 90. And down below, the one that most of us forget, is 270. So we can see that if we've gone from here to here, so basically this, if we're starting off here and we go up here, that's a 90-degree angle that we've just made. Now, what about other important degrees on the unit circle? Well, what if we split between 0 and 90? What would that halfway point be? We know that that's 45. We can do that in each one of these 4 quadrants, and that's why a 45, 45, 90 triangle is so special. We can also go up 30 degrees or 60 degrees and create the 30, 60, 90 right triangle. So that's what we're going to look into next. So if we go out 45 degrees from here, what we can do is plot that point and then drop it straight down, and we see what we've created is a 45, 45, 90-degree angle. That's one of the 2 types of special right triangles. What about if we go out 30 degrees? We can plot that point, drop a perpendicular, and we've created a 30, 60, 90-degree triangle. And then if we did that same thing but went out 60 degrees instead, it's the same triangle, just a little bit flipped. So if we went out a grand total of 60 degrees and dropped a perpendicular, we also have a 30, 60, 90 right triangle. All right, I'm putting a lot on this first slide because I want to just show you kind of where these triangles come from. Our 2 special right triangles are the ones I just talked about, the 45, 45, 90-degree triangle and the 30, 60, 90-degree triangle. Understanding those will help us understand the unit circle as a whole. Okay, the last main thing that we have to understand before we put this all together is that so far we have only talked about degrees. And I start with degrees because it's what we all kind of know, right? We learned from a young age that going all the way around in a circle is a 360 and halfway is 180 and so forth. But the unit circle also deals with radians, and those are the measurements that have pi in them. So you probably remember like pi over 2 or 3 pi over 4, things like that. Radians are just a way that best express the measurements on a circle. So degrees work very well, but kind of the language of the unit circle is in radians. So if we can accept that all the way around the circle is 360 degrees, we can also say that all the way around the unit circle is also 2 pi. And it's getting a little crowded over here, but this area is also 2 pi, which I'll write over here. So going all the way around the unit circle is 2 pi radians. Now there's a reason behind this. 1 radian is approximately like 57 degrees, and so 2 pi of those radians gives us approximately 360. Okay, so then if all the way around the unit circle is 2 pi, that means halfway around the unit circle is 1 pi, or just pi. So 180 degrees is also pi. That means that halfway to pi at 90 degrees, that's half of a pi, or pi over 2. And since each one of these quadrants, or each one of these 90 degrees is a half a pi, we have a half a pi, another half a pi, and then we have 3 halves of pi, or 1.5 pi's. We can write that as 3 pi over 2. And then, of course, all the way around is also 2 pi. Now, this location is also called 0 because it's the start. Okay, so we have found that we can measure these locations in both degrees and also in radians. Now, how do we go between degrees and radians? We use a unit. We are going to use the fact that 1 pi is equal to 180 degrees. So if we want to go from degrees to radians, we want to multiply by pi over 180. If we want to go from radians to degrees, we multiply by 180 over pi. Now, why can we just multiply by this? Because this is equal to 1. These two things are the same, right? They're the same spot. They're the same amount. And so we can multiply by just something over itself because that's just a big fat 1. Let's do a quick example. Let's say I want to prove that 270 degrees is in fact 3 pi over 2. All right, so we'll start with 270 degrees. And then since we're going from degrees to radians, we'll multiply by pi over 180. Basically, we want the degrees to cancel out. So when we multiply by pi over 180 degrees, I could write 270 degrees as 270 over 1, right? We can write anything over 1 if we want. And then we'll see that the degrees will cancel. And when we're multiplying fractions, remember we multiply straight across. However, instead of just multiplying straight across first, what we can do is cross cancel. So any top to bottom, if you can cancel anything out, go ahead. And since we have zeros here, we can divide both of these by 10 and cancel out the zeros. Then we have 27 over 18. Those are both divisible by 9. So we'll divide 27 by 9 and get 3, 18 by 9 and get 2. When we multiply straight across the top, we'll get 3 pi. And when we multiply straight across the bottom, we'll get 2. So 270 degrees in radians is 3 pi over 2. Let's try another example. Let's figure out what 60 degrees is in radians. So 60 degrees is like right here. So we know it's between 0 and pi over 2 radians. And so we know that it's going to be smaller than pi over 2. So let's take 60 degrees, and we want to figure out what that is in radians. So we'll multiply by pi over 180. So once again, the degrees will cancel. Again, we want to be left with something in terms of pi. We can divide both top and bottom by 10 by canceling the zeros. And 6 over 18 can be canceled. They're both divisible by 6, so we'll divide them both by 6. So we'll have 1 pi over 3. So 60 degrees is pi over 3 in radians. Okay, let's try going the other way. So we're going to start with a measurement in radians and figure out how many degrees it is. 5 pi over 3. This is larger than a whole pi, right? It's 5/3 of a pi. And so it's definitely more than a pi. So this is like 3/3 of a pi, right? One whole pi. And then if we keep going, 5/3 of a pi is almost 2 pi, right? 6/3 pi would be 2 pi. So it's almost all the way around the unit circle. So I'm going to guess, it's somewhere around here. So we know in degrees this should be a little bit bigger than 270, but not quite 360 based on this amount, right? Because all the way around is 2 pi, and this is a little bit less than that. So let's actually see exactly how many degrees it is. So we'll start with 5 pi over 3. And then in order to convert from radians to degrees, we just go the other way. We want the pi to cancel this time. So we want to multiply this time by 180 degrees over pi. And so the pi's will cancel. And then we can cross cancel top to bottom. We can see that 180 and 3 are both divisible by 3. I know that because 18 is divisible by 3. So 18 divided by 3 is 6. So 180 divided by 3 is 60. Put a 0 on it. So this is 60. And 3 divided by 3 is 1. So when we go straight across, we'll do 5 times 6, which is 30, and then put a 0 on it. So 300. And then we don't have a denominator because it's just 1, so 300 degrees. And that makes sense. It's a little bit past here. All right, so this is just going back and forth between the two ways to measure locations on the unit circle. So again, we start here on the unit circle. This is our 0, either in degrees or radians. 0 is 0 no matter what. And if we go up and around, all the way around is 360 degrees or 2 pi. Degrees will always have a degree symbol, and radians will have a pi in it. We can convert between degrees and radians using this unit. Pi and 180 are the same, so we can use that to convert. All right, let's talk about a special spot on the unit circle, one that I have already alluded to, and that is halfway between 0 and pi over 2, or between 0 and 90 degrees, which we know is 45 degrees. Let's figure out what the radians of 45 degrees are. So if we take 45 degrees, in order to figure out that in radians, we'll multiply by pi over 180 degrees. And doing that math, that'll give us pi over 4. So this location is pi over 4. And then if we drop a perpendicular, creating this special right triangle, we have the 45, 45, 90 degree triangle, otherwise known as the pi over 4, or just the pi over 4 right triangle, since 45 degrees is pi over 4. Let's explore this triangle. So we've already determined that the coordinate points on these 4 spots are consisted of, like 1, 0, 0, 1, and so forth. But what about these coordinate points right here? We don't know what these coordinate points are here, and that's important. We want to know because 45 degrees, aka pi over 4, is an important spot. It's halfway in each quadrant. So let's figure out what those coordinate points are. So what I've done is I've taken this triangle right here and I've blown it up down here. And so instead of 45 degrees, what I'll do is I'll write pi over 4, and this is the pi over 2, or 90 degrees. So this is our first special right triangle. Definitely make sure you have this drawn out. So let's figure out what these coordinate points are. Basically, this coordinate point is right here. Okay, so I want to know from the origin, how far do I go in the x, and then how far vertically do I travel up? So this length and this length. Well, we know this length right here. The radius is 1 of this circle. So I know that this length right here is 1. What else do I know? Because it is an isosceles triangle, this length and this length are the same, so we can call that length x. Let's figure out what x is. Using the Pythagorean Theorem, we'll have x squared plus x squared is 1 squared. This is 2x squareds. Divide by 2. So right now I am just figuring out, I'm deriving what these lengths are. This is just a way that you can derive it and you don't have to memorize. Take the square root. Now normally when we take a square root it's plus or minus, but this is a length, it's a distance, so it's just going to be positive. When we take the square root of a fraction, we take the square root of the numerator and the square root of the denominator. And in math we don't like roots in the denominator, so we're going to go ahead and rationalize that. So we'll get root 2 over root 4, which is plain old 2. So this length right here is root 2 over 2. That's what our x value is. Cool. So this is our first special right triangle. This is the pi over 4 special right triangle. Now, do you have to have this part memorized? No. This is what you need to know. However, I don't love memorizing things. I like to derive them. And so if you truly understand, what we're doing, you don't have to have this memorized. You can figure it out on your own. But that's how we get these measurements right here. And that's why this special right triangle has these 3 measurements. All right, the next special right triangle that we are going to explore is the 30, 60, 90. This one's a bit harder to prove, so just bear with me here. This is the 30-degree angle. Let's figure out what that is in radians. So if we take 30 degrees and we multiply it by pi over 180 degrees, we'll get pi over 6. How about the 60-degree angle, the one right up here? Earlier we found that 60 degrees was pi over 3. Okay, so this is our 30, 60, 90 special right triangle. And it's kind of weird, but the 30-degree angle is pi over 6, and the 60-degree angle is pi over 3. They're kind of swapped in your brain, but if you think about it, a sixth is smaller than a third. It's actually half as much. So this is the 30-degree, and that's the 60-degree. All right, once again, we know that our radius is 1 because that is the definition of the unit circle. It has a radius of 1. So we know that this length here is 1. However, we don't know these lengths here. It's a much longer proof to prove, well, it's not too long, but if you think of this, if you extend this down and create an equilateral right triangle, if you doubled this side length, it would also be 1. Not going to get super into it, but this is half of the side length. So this is half. Once again, I'm not going to do that entire proof because I want to keep this as quick as I can. But if you just remember, obviously the radius is 1, and the shortest side length of this special right triangle is half of that radius. We can use the Pythagorean Theorem to find the length of the third side. All right, so we'll have one, and I'll call this x, since it is x. It's this length right here along the x-axis to find these coordinate points here. All right, so we'll have x squared plus 1/2 squared is 1 squared. And then 1/2 squared is 1/4. Square the top, square the bottom. Oops. I didn't mean to put an equal sign here. Then if we subtract 1/4, we'll get 3/4. And then we take the square root of 3, and then square root of 4. So this length right here is root 3 over 2. All right, so you definitely should have written down your 2 special right triangles. This is one special right triangle, the 45, 45, 90. These are the side lengths. This is the second and the only other special right triangle, the 30-degree, 60-degree, 90-degree special right triangle. I have the angles marked in radians because that's what we'll see more often this year in calc. And then these are these 3 side lengths here. So here are your 2 special right triangles. What do these mean? Well, if we look at this 45, 45, 90, actually let's look at the 30, 60, 90 because that one's still drawn on here. In order to get from our origin to this coordinate point here, we're moving to the right root 3 over 2, and then we're going up 1/2. So this coordinate point right here, these coordinates are root 3 over 2, comma 1/2. Then with the 45 degrees, if we travel 45 degrees, these coordinate points, here's the origin. If we go over root 2 over 2 and up the same, so over and up, the x-coordinate and y-coordinate to get to this point on the unit circle are the same, and they're both root 2 over 2. Now, we can fill in the entire unit circle using these two special right triangles. Using these special right triangles, we can find all these coordinate points on our unit circle. So this is the 30 degree. I just don't have the whole triangle drawn in, but we know now how we got these coordinate points. Here's our 30 degree mark at pi over 6. The x-coordinate's 3 pi over 2, which is almost 1, and then we go up only half. This coordinate point here at 45 degrees, we go over square root 2 over 2 units and up square root 2 over 2 units for the x-coordinate and the y-coordinate here at pi over 4. Pi over 3, 60 degrees, is just the same triangles here, just flipped. So we only go half unit, and then we travel upwards root 3 over 2 units. These two are just flipped because they're actually the same special right triangle, that 30, 60 degree right triangle. And so we can actually fill in the entire unit circle using this, using these ideas. So if we flip from pi over 4, that's probably the easiest one to see. It's the halfway. If we go here, halfway between pi over 2 and pi, between 90 and 180 degrees, we're at 135 degrees. And if we think about 135 degrees, like how many radians it is, we could actually figure out how many radians it is. I want to make that go exactly halfway. There we go. Or we can just think about splitting up pi. So this is 0 pi, this is a fourth of a pi, this is another fourth of a pi, this is another fourth of a pi. It's 3/4 of a pi. So this is, this is 3 pi over 4. And then if we go another fourth of a pi, we've gone 4/4 of a pi, or 1 whole pi. Now, if we think about traveling, it's basically the same coordinate points as this original pi over 4, except from the origin we've gone left and then up. Therefore, the coordinate points here at 3 pi over 4 are negative root 2 over 2 since we're going left, and positive root 2 over 2 since we're still going up, so the y-coordinate's still positive. We can fill in the same thing in quadrants 3 and 4. So if we look at these next two pi over 4, members of the family, basically, again, we saw that if we travel 4 pi over 4s, right, 4 quarters, we're at 1 whole pi. And then if we travel another quarter of a pi, we get 5 pi over 4s. And then if we travel another 6 pi over 4s, which simplifies to this, then another, we have 7 pi over 4s, and then the last one is 8 pi over 4, or 2 pi, all the way around. So basically, we've just quartered this, and, well, it actually has 8 of those, because all the way around is 2 pi. So we can see that the x and y coordinates are basically the same for all of those pi over 4 members of the family. However, depending on if you're going right, up, left down, or right and then down, the positives and negatives change. So for example, 7 pi over 4, we're going in the x direction positive, right to the right, but then we're traveling downward, so the y coordinate is negative. We can do the same thing for the pi over 6 and pi over 3 families. Okay, so I've filled in the second quadrant. Whoops. There we go. I filled in the second quadrant. It's getting a little messy because I made this so small, but if we take a look, this is 1/6 of a pi. This is another sixth of a pi. It's 2/6, which is 1/3 of a pi, pi over 3. Basically, 1/6 of a pi, right? Pi over 6 was 30 degrees. So this is 30 degrees, 60 degrees. Here's another sixth. 3/6 is a half. 4/6 of a pi is 2/3 pi, a 5/6, 5 pi over 6, and then a 6th, it's hard to say sixth, 1 whole pi, there we go. And if we do that again and split this into 6ths, then we'll get another whole pi over here. So take a look. Pi over 6 over here is the part of the 30, 60, 90 triangle, so is here. And these are all positive values because it's in the first quadrant. But when we travel to the second quadrant, they're the same, right? They're reflected, except we're going left and then up for both of these. So the x-coordinate's negative and the y-coordinate is positive. I realize this is a lot in one single video. But I just wanted to show you the symmetry of the unit circle and also how those special right triangles allow us to find what the coordinate points are on that unit circle. The last thing that we're going to talk about today is the equation of the circle and how that relates to sine and cosine. So the equation of any circle is this. You don't need to write this down. Those are squareds. All right, so h and k are the center of a circle, and r is its radius. And for the unit circle, the center is 0, 0. So h and k are 0. The radius is 1 of the unit circle, so r is 1. So the equation of the unit circle is just x minus 0 squared, which we don't even need to write the minus 0. Same with the y. And then 1 squared is just 1. And so this is the important equation of our unit circle. Do you remember SOHCAHTOA? Well, we're only going to worry about SO and CA, so SOHCA. And if we take a look at any right triangle, if we're talking about a certain angle in that triangle, remember that this is the opposite side, and this is the adjacent side, and this is the hypotenuse. Well, in order to get sine and cosine, we take a look, and sine from an angle, right? If we're looking at this angle, like if I were to just take this triangle here, the angle's down here, bottom left, the sine is the opposite over the hypotenuse. Well, in the unit circle, what is the hypotenuse? What's the radius? It's 1. So sine is really just the opposite, or the vertical side of this triangle. If you look at the cosine, cosine of this angle is the adjacent side divided by the hypotenuse, which is 1. And so our cosine of this angle is the adjacent side, or the x-coordinate here, how far we're moving along horizontally. That is why any xy coordinate on the unit circle, we said that the x, the horizontal, is the cosine, and the y, the vertical distance traveled, opposite, is the sine. So, if we wanted to find out, let's say, what the cosine of a certain angle is, you just have to look at its x value. So let's find the cosine of pi over 6. Well, the cosine of pi over 6 would be 3 pi over 2, because cosine from here, this is our angle, pi over 6, it's adjacent over hypotenuse. The hypotenuse is 1. So the cosine is the x value, it's 3 pi over 2. Let's find the cosine of 3 pi over 2. Where's 3 pi over 2? It's down here. Cosine is the x value. The x value at 3 pi over 2 is 0. So the cosine of 3 pi over 2 is 0. Let's find the sine of an angle. Let's do the sine of 3 pi over 4. Where is 3 pi over 4? It's right here. The sine is the y value. The y value at 3 pi over 4 is root 2 over 2. Let's do one more. Let's find the sine of 90 degrees. Where is 90 degrees? It's right here. Sine is the y value. The y value is 1. So that's a lot in one video, I do realize that, but if you understand the unit circle and that degrees and radians are just ways to mark angle measures and different spots, if you will, on the unit circle. You can convert between degrees and radians. Each one of these points on our unit circle is a point in the coordinate plane, and they all have xy coordinates to them. They relate to trig in a sense that the x-coordinate of any angle is the cosine value, and the y-coordinate of any angle is the sine value.